Okay, in this video we are doing Calc AB Problem Set 100. The problems and a playlist are in the description below. We made it to number 100. Good for us. Let's look at the problems. All right, we want to evaluate d dx of the integral from 0 to x cubed cosine of t squared dt. All right, so this is the second fundamental theorem of calculus. What we're going to do is we're going to take the upper bound. The upper bound has to be the variable. We're going to take the upper bound and we're going to plug it into the integrand. So every t becomes a x cubed in this case, so we're going to get the cosine of the quantity x cubed and then squared times the derivative of the upper bound. The upper bound is x cubed, so the derivative is 3x squared. And then I think you would probably rewrite this as 3x squared cosine of x to the sixth. That is the derivative of that accumulation function. Let's take a look at the next problem. So if g of x, I guess we're doing accumulation functions today. If g of x is 5x squared minus 3x plus the integral from 2 to 2x e to the t cubed dt, we want to find the equation of the line tangent to g of x at x equals 1. So if this was at anything other than 1, I think we'd kind of be in trouble because of that definite integral we'd need to evaluate, but it's at 1, so we're good. So g of 1, every x becomes a 1, so we're going to have 5 minus 3 plus the integral from 2 to 2 of e to the t cubed dt. The integral from 2 to 2, or just in general from a to a, of anything is 0. So really this is just 5 minus 3 plus 0, and 5 minus 3 is 2. So g of 1 is 2. And then we also need to find g prime. So we're going to do some power rule, so 10x minus 3. Then we're going to use the second fundamental theorem, right? So we're going to take the upper bound, which is 2x. We're going to sub it in for every t that we see. So e to the t cubed becomes e to the quantity 2x cubed. Then we'll multiply by the derivative of the upper bound, so multiply by 2. And that's our derivative. Now we need to just plug 1 into this, so instead of simplifying, I'm going to just plug in 1. G prime of 1 is going to be 10 minus 3 plus e to the 2 cubed, which is 8, and then times 2. So we get ultimately 7 plus 2 e to the 8th. So that's like very, very steep. Doesn't really matter because we don't have to graph it, but like e to the 8th is huge. So the tangent line in point slope form is going to look like y minus 2 equals quantity 7 plus 2 e to the 8th, quantity x minus 1. That's our tangent line. It's a little weird looking, but I think we did it correctly. Next up, use a table of values for the differentiable function f to answer the questions. We want to approximate f prime of 7. So we know that to approximate a derivative, we have to use the approximately equal to sign. So f prime of 7 is approximately. In the table, 7 is in between 6 and 8, so we'll use the slope of the secant line on that interval. So we have f of 8 minus f of 6 over 8 minus 6. F of 8 is 3, f of 6 is 7, so 3 minus 7 is negative 4. So we have negative 4 divided by 2, which is negative 2. So that's approximately f prime of 7. Is f prime of 7 that? We have no idea. Like it might be, but it also might not be. All right, B. Using a left sum to approximate the integral from 1 to 8 of f of x dx gives a value of 45, and we want to find the value of k. So if you look in the table, f of 3 is equal to k. So we're going to try to figure out what f of 3 is here. First, let's just do the left Riemann sum. So our integral is going to be approximately. So you got to, anytime you're approximating, you got to start out with the approximately equal to. All right, we're going from 1 to 3. That's 2. The left endpoint is 5. So 2 times 5 plus. We're going from 3 to 6, so that's a distance of 3. The left endpoint is k. So there's our k that we're going to solve for. Then we go from 6 to 8, which is a distance of 2. The left endpoint is 7. So we have this, so that's 10 plus 14 is 24 plus 3k. All right, so the left sum is 24 plus 3k. We also know in the problem that that should be equal to 45. So I'm just going to set 24 plus 3k equal to 45. And then I will subtract 24 from both sides to get 3k is 21, and then divide by 3 and get that k is 7. That's kind of a nice problem. I like it. It's got like a little, you have to do a left sum, and then you also have to solve something, kind of combining a couple ideas. Let's take a look at the next thing. If the tangent line at x equals 3 is y equals 5x minus 7, what is the value of k? I don't know. Like this is kind of a lame question, but we just need to know that the point of tangency is on both the line and on the function. So if I just plug 3 into this tangent line, that should tell me the y value on the tangent line, which is also the y value on the function. So this is 15 minus 7, so 8. So y is equal to 8 on the tangent line. That's the point of tangency, so f of 3 is also 8. It's not the best problem in the world, but it does make you think for like half a second maybe, and that's kind of the goal with the problem sets. All right, if h of x is e to the f of x and f prime of 1 is 3, find h prime of 1. Okay, so we're going to need to find h prime of x first, and this is a chain rule problem. So h prime of x is going to be e to the f of x times the derivative of f of x, so times f prime of x. Then we're going to plug 1 in. So if we plug in 1, we get h prime of 1 equals e to the f of 1 times f prime of 1. There's a lot of calculus problems which are basically like, can you read a table? And I think we can, right? F of 1 is 5 from the table. F prime of 1 is 3 from the given information. So we're going to have e to the 5th times 3. So, you could leave that. There's nothing really wrong with it, but I think traditionally you would write it as 3e to the 5th. All right, that ends the 100th problem set. So I hope this was helpful, and good luck.